Consider the following arithmetic sequence: 1, 3, 5, 7, and so forth. Let's find the explicit form for this one. an is equal to a1 plus dn minus 1. Now, of course, we know that a1 is equal to 1 from here, and the common difference is 2. So we say a of n is equal to a1, that's 1, plus d, that's 2, n minus 1. I distribute the d. Now if I flip the two terms around, I will get a of n is equal to 2n minus 1, and this pretty much looks like something that you probably already know. Y is equal to mx plus b, the linear equation form, where 2 is the slope and negative 1 is the y-intercept. So in other words, if you plot the points of a sequence on a graph, it will have a linear form. 1, 3, 5, 7. I mean, let's say the y-axis represents a of n and x-axis represents n. So the first term, so this is a1, that's 1 here. So the first term is 1, so I'm here. So the first term is 1, I'm here. And the second term is 3. So the second term is 3, I'm here. That's 3. So that's 3. That's a2. And a3 is 5. So the third, so this is 1, this is 2, this is 3. The third term is 5. So 5 is here. So this is 5. And the fourth term, that's 4. The fourth term is 7. So I'm here, 7. So as you can see, if I keep going, I will have some kind of a linear pattern. So I have a linear pattern where the slope is, of course, 2. And of course, remember, 2 is our common difference. How about the geometric sequence? So the geometric sequence, here we have, so for the geometric sequence here we have a of n is equal to, so in our case, a1 is 1 and the common ratio, r is 2, because you are multiplying by 2 each time. So I will say a of n is equal to a1, which is 1 times r, 2, n minus 1. This is an exponential form. So let's put it on the graph as well so we can see how that looks like. The numbers that we have are, first number is also 1, the second term is 2, the third term is 4, and the fourth term is 8, and the fifth term will be 16 here. If we were to draw a line connecting the points, it would have an exponential form. It will look pretty much like this. Another thing to consider is, the arithmetic form a1 plus d n minus 1. But why is that? Let's see if we can think through this. a1 is of course a1, but a2 will be a1 plus d. That's what the recursive formula tells us. And a3 will be a2 plus d, so that means it will be a1 plus d plus d. a4 will be a1 plus d plus d plus d. So how many d's do we have here? It's 3. It's always going to be 1 less than n. So that's why we say a of n is equal to a1 plus d times how many I have of them. So in this case, it's 3d if n was 4. But to generalize, I would say it's times d n minus 1. That's where it comes from. Thinking about the geometric sequence, first term, of course, the second term is the first term times r. The third term is the first term. So again, we see that here we have, how many r's we have? It's 3 of them, but here we have 4. So the number of r's that we are multiplying will be always 1 less than the term that we're talking about. So to generalize, we say an, this one, is equal to a1, this one, times r. However, r is being multiplied by itself so many times. How many times? N times minus 1. And that's where these formulas come from.